Hello everyone. So today we are going over concept 3-12, frictional force. We're going to just be going through all the questions related to 3-12. And as always, I want to make sure you have your calculator on you as well as your formula sheet, as that makes this whole process of going through these questions a lot easier. So, okay, quiz question 3-12, question 1. The force of kinetic friction between two objects in contact depend on which of the following? So right away, I want to illustrate the equation for kinetic friction. So kinetic friction, the force of kinetic friction, is equal to some coefficient of friction, kinetic coefficient of friction, times the normal force of the object. So if you have a 20 kilogram box, 20 kg, and it is in contact with the floor completely, it has a downward acceleration of 9.8 meters per second squared. That is the gravitational acceleration. And then the opposing force, to make sure it doesn't break through the ground, is the normal force. And the normal force would be equal to the gravitational force. So the gravitational force is equal to 20 times 9.8, which is equal to, let me put it in the calculator, 20 times 9.8, 196 newtons. 196 newtons. So these are equal to one another, the little dash line. Imagine this is a straight line. I can't draw straight. So this equation is essentially saying the force of friction when an object is moving is equal to some coefficient of friction times the normal force of the object acting upon the object. So therefore, when we start analyzing these answer choices, I want you to keep that analysis in mind. So part A says the force of kinetic friction depends on the normal force between the two objects. As we just said, the force of friction depends on that normal force that is taking place. And if we imagine a 20 kilogram box versus a 100 kilogram box, the force of the normal force acting upon this box is greater than the 20 kilogram box. Hence why you would need to exert more force to get it moving and keep it moving. So force 2 would have to be greater than force 1. So A is true. If we look at part B, how fast the objects are moving relative to each other. So in this equation, we can analyze this both through the equation and just through common sense. Through the equation, do we have the inclusion of some multiplied value of velocity? The answer is no, we don't. So we get rid of that. So right away, we know that velocity is, or the frictional force, the force of kinetic friction is independent of velocity. It is independent. Independent of V. So right away we can cross off answer B. But also just imagine when you get something moving, when you're pushing like a shopping cart, right? Does it ever get harder to push suddenly when you're, or easier to push when it's speeding up? You generally put about the same amount of force consistently when the object is moving. So therefore, it would not make sense that the speed of the objects changes the force of kinetic friction, because it'd be consistent. It'd be the same throughout. So part C here, we're moving on, says the surface area of contact between two objects. So I want you, if you have it nearby, I want you to grab a tissue box. And I want you to just kind of push it across your desk with the longest side down, and then push it on your desk with the stubbiest side, the shortest side down. And I want you to just examine how much force it takes to push it in both configurations, because the surface area contacting the desk is different in both cases. And if you did this, you would note that it takes about the same amount of force. The force would be equal to push the object in both cases. Also, looking at this equation, there's no inclusion of surface area in the equation itself. meaning that the surface area does not play a role in the amount of force required to calculate the force of kinetic friction. Now, part D, the materials the objects are made of. So we're going to imagine two boxes for this one. They're both 20 kilograms, but one is on ice and one is on carpet. And just through your experience, which one would be easier to push? The answer would be ice. It's easier to push it on ice. That's because even though the normal force of the object is the same, the coefficient of kinetic friction here changes between these two surfaces. So the interactions between the box and ice is different than the interactions between the box and carpet. And as such, it impacts this equation in that it changes this coefficient here, meaning this coefficient is smaller on ice and greater on carpet. So therefore, the materials the objects are made of does play a role in the force of kinetic friction between two objects. Okay, so moving along here, we are going through and answering 3-12A. A box on a rough surface has a weight of 100 newtons. If you recall, weight is equal to the mass of an object times its gravitational acceleration. And if a box is not accelerating in the vertical direction in any way, so if the force acting in the y component is equal, then the normal force is equal to the weight of an object. And as we can see here, it appears that the block is not falling, so therefore the normal force must also be equal to mg. So the normal force must be equal to mg, which is 100 newtons. You apply a horizontal force, P, of positive 12 newtons. So we're already, when we're looking at this, we're taking the direction of the object into account. But the box doesn't move. Oh, how strange. What is the static friction force on the box? The static friction coefficient is 0.25, so it's listed right here. So first, already on your equation sheet, you should see this equation that I wrote out here. Fs max is equal to the static frictional coefficient times the normal force. And this helps us to calculate the maximum amount of force before an object begins to start moving. So if we just plug in the values given in this equation, we see that 0.25 times 100 equals 25 newtons. So we would need to be applying a force greater than 25 newtons in order for this box to begin moving. And because the force given in the problem is less than, so 12 is less than 25, this box will not move because it does not overcome the static frictional force of the object. And I want to take a moment here to take a second and look at what this means. If we're saying that the frictional force is always 25, it's not. But if we took a second to say it is always 25, that means when an object is at rest, it is being acted on by a frictional force of negative 25 newtons, so negative 25 newtons. This would mean that it's always moving backwards. And if we just look around us, nothing's moving. So the frictional force must be dependent on the fact that a force is being applied on an object. So when P is being applied, the frictional force is also interacting as well. The frictional force only plays a role when a force is being applied to an object. So therefore, if we do not overcome the static frictional force, that must mean that the force applied is equal to the frictional force. So with that in mind, if P is positive 12 and the box is not moving, we can say that the net force in the x direction is equal to 0, and 0 equals 12 plus some value. And at that point, we can just plug in these values, and we find that 12 plus negative 12 equals 0. And that's the correct answer. Answer A does not properly consider the direction the force is being applied on the object. So that's why A is false. C only does not consider direction, as well as it is plugging in the Fs max. It's not considering that the force actually being applied on the object. If we had a plus 25 newtons, we would say that the object is moving with a force of 37. Oh, that is an M. 37 newtons. And then D, negative 25, we would be saying that there's a net force. If we balance these two out, there's a net force of negative 13 newtons, which would mean that the box is moving in the negative direction, which from the problem statement, we see that the box is not moving. So that is why the answer is B. And then E, the frictional force cannot be determined. It can't. This is just a trigger. I hate that one. Okay? Hope that makes sense. So moving along here, we have the last question for this set. We have lecture question 3-12D. And it says, a skier is going down a hill. The hill is not frictionless because the skier is moving at a constant speed. That means, so this already, V equals, is not changing. So let me change that. V is unknown, but it's non-zero. A equals 0. The skier's mass is 60 kilograms, and the hill is at an angle of 15 degrees. What is the coefficient of friction between the skis and the hill? So right away, which equation would we be using? Would we be using the one for static friction or kinetic friction? The answer is kinetic friction, and that's because the skier is moving, so it must have overcome the static frictional force in order to begin moving, and now the force of kinetic friction is being applied onto the skier. So when we look at this, I always like to make a free body diagram of what's going on. So we have this little dot. This little dot is our skier. The skier is experiencing its weight, its gravitational from the gravitational acceleration. So weight force here. So this is 60 times 9.8 to equal 588 newtons. We know that there's some normal force being applied between from the slope and the skier. So that one's at an angle. And this is the normal force. And then we know there's some frictional force taking place because in the problem it says the hill is not frictionless. So this is occurring at an angle, and that angle is equal to the angle of the slope. So this is Fk, the kinetic frictional force. Okay, so if we look at this slope here, and we look at our free body diagram, we see that this angle here is 15 degrees because the slope is 15 degrees and the frictional force is in line with the slope. So what we can then do is we can kind of adjust this free body diagram. We can rotate it a little to make it a little easier to parse, okay? So we can rotate this exactly 15 degrees, and we can say that the normal force is straight up. The frictional force is at a 90-degree angle because these are at a 90-degree angle to one another because they're perpendicular. The normal force is perpendicular to the surface that you are in contact with. So you can see 90-degree angle. So this is F sub K. And then if we rotated everything else 15 degrees, we see that our weight, which was equal to 588 newtons, is at a slight angle. And we know that this angle now is 15 degrees. So looking at this, if we know there's a constant speed, we also know that no acceleration is taking place, which means that all of these forces cancel out. So the net force in both directions, F net, is equal to 0 in the x direction and in the y direction. So therefore, we need to see, since the weight is at an angle now, we can break this down into its y component and its x component. So let's just draw a nice little triangle here. So we know that the hypotenuse is 588 newtons. We know that the angle is 15 degrees. Is there an equation that we can use that helps us find the vertical and the horizontal components of a triangle? The answer is yes. So for vertical, we'll say y. Y is equal to 15 is equal to the hypotenuse, so 588 cos 15. And then x, so this is x now, x is equal to 588 sine 15. And these are just rules of triangles. If you don't recall why I'm using these values, then just review SOHCAHTOA, basically. Okay, so from here, we plug in chug. We see that y is equal to 567 newtons approximately, and x is equal to, give me 1 second here, 152 newtons. 152 newtons. And if we look at this, let's reanalyze this one more time. So we broke this down into its vertical and horizontal components. So I'm just going to plug in these. Instead of one hypotenuse, it's the vertical and horizontal components. We know that because velocity is constant and not changing, the horizontal and the vertical components must cancel out one another. So we know that the downward vertical component is 567 newtons. So the normal force must be 567 newtons. We know that the x direction has a force of 152 newtons. I almost wrote 125. 152 newtons. So the frictional force must be 152 newtons in the negative direction. So now we can plug this into the equation. The kinetic friction is equal to the kinetic frictional coefficient times the normal force. We know that the normal force is equal to 567 newtons. We know that the force of friction, the force of kinetic friction, is 152 newtons because they cancel out, so therefore it's equal to 152 newtons. So we can just plug in and solve for m sub k. So 152 equals 567 mu k. That is an awful mu, I'm so sorry. And from there, we just divide 152 by 567, and that equals approximately, because we're rounding, 0.27. And that is our answer for mu sub k.